Well, I believe this is the beginning of my recorded talk, so I would like to thank Kumar Murthy and the Fields Institute for inviting me to participate in this experiment. This is an introduction to the material I will be talking about next Wednesday, what conventionally it would call a live presentation on the local Langlands correspondence for the exceptional group G2, which is joint work with Kari and Thorne. And I'll have more to say about that next week. But in the meantime, here is a general presentation of the Langlands program from the point of view of somebody who wants to understand why one might want to study the local Langlands correspondence. So apologies to those of you who are familiar with this material. It's meant to be introductory. Here it's in several different sections. So let's begin. And the beginning is Galois theory. You can start from either end of the Langlands correspondence. It has two parts. It relates to things. One of them has to do with Galois theory, and the other one has to do with automorphic forms. And I'm going to start with Galois theory. So everybody who learns Galois theory, but not everybody learns what you can do with it. There's at least one thing that, one calculation that people do study. So you can compute the Galois group. That's what Galois theory does. It tells you how to compute a Galois group. And you can compute the Galois group of the set of roots of polynomials, not very many polynomials, it turns out, but at least this one, the cyclotomic polynomial, whose roots are L to the nth roots of unity. And L, I didn't tell you what L is, it's a prime number. And we're going to give a name to the set of roots. The roots, call it mu L to the n. These, if you think of them as complex numbers, then they are the vertices of the regular polygon inscribed in the unit circle with L to the n sides. So they're L to the n vertices. And that makes it, shows it's a cyclic group, order L to the n. And the Galois group acts by automorphisms, permutes the generators. It takes a generator to another generator, and the automorphisms of mu L to the n is the multiplicative group of Z mod L to the n. All right, that's basic Galois theory. Now here's a clever idea, it's not my idea. This starting point for a systematic study of Galois representation. Not the only thing you can do with Galois representations. Suppose you act on all these mu to the L to the n together. Well, you calculate, this is a union, it's not a disjoint union because L to the nth roots are also L to the n plus first roots, so it's an increasing union. And when you work it out, it turns out that the automorphism group is the multiplicative group of ZL. What is ZL? It's the compact topological ring that you get by taking the inverse limits of Z mod L to the nz for all n. And this way, what do? We get a homomorphism from the Galois group to the multiplicative group of a ring, which we can think of as GL1 of that ring, which is contained in GL1 of its fraction field. All right, so this is a one-dimensional representation of the Galois group. I call it omega L. Now that's just one example. Now suppose we take an elliptic curve over Q. Here's the equation of elliptic curve. A and B are rational numbers. It's a cubic equation. And it's one of the first thing you learn about elliptic curves is that the set of solutions, complex solutions, is an abelian group. And you can even identify it with the quotient of the complex numbers, the additive group of complex numbers, by a lattice, lambda. Lambda is just a rank 2 free abelian group. All right. So the elements of order L to the n in this complex group modulo the lattice, you can think of this as R2 mod Z2 as at least as an abstract group. So the elements of order L to the n are just Z mod L to the n squared, and Galois group acts on that. So this is what are the automorphisms of Z mod L to the n Z? Well, it's GL2 of Z mod L to the n, but we're going to apply this clever idea, which arose in the early part of the 1950s. And we have a homomorphism to the automorphism group, which is now GL2 of ZL, which again is contained in GL2 of QL. So we get a two-dimensional homomorph representation of the Galois group. Now let's be as general as possible. We want to take X to be an algebraic variety defined by polynomials in the n+1 variables in the projective space with rational coefficients. Well, the set of points with complex coordinates is a topological space. And for any positive integer I, the theory of état cohomology provides an action on this rational cohomology when you tensor it with QL, and you get a homomorphism, we'll call it rho I XL, into the automorphisms of some vector space. Let's say this is a vector space. It's an L-adic vector space, and it is a vector space of dimension m. And now I'm going to absent myself for a moment because I don't have a clock. Well, so starting from an algebraic variety, we get just a set of polynomial equations. We get a topological space. We look at its cohomology. We tensor with QL. L is any prime number. And for each such L, and for each degree of cohomology, we get a homomorphism, that is to say, an m-dimensional representation of the Galois group for some m. So, well, there are a lot of algebraic varieties, and so there are a lot of homomorphisms. And so the Galois group has a lot of quotients. These are just some of them. There are other ways of looking at the Galois group. In fact, these Galois representations have special properties. They are called geometric. Well, that is just a code word, which I'm not going to explain, but you can sort of see why we would call them geometric, because they come from algebraic geometry. Here is a conjecture. This is a very vague version of one of the Fontaine-Mazer conjectures, which motivates a great deal of research in algebraic number theory. Any homomorphism, any n-dimensional representation that is geometric, occurs in the cohomology of some smooth projective variety. Now, I didn't say that this is a smooth variety, but we could assume that it is a smooth variety, a non-singular variety. And occurs means would mean that it is an irreducible summand, or let's be more cautious, an irreducible constituent, Jordan-Holder constituent for the representation of the Galois group on one of these spaces. All right, so that's the conjecture. If you have a homomorphism that has this enigmatic property of being geometric, then it actually there is some variety somewhere, generally more than one, which has the property that that you can recover this representation in its cohomology, one of its cohomology degrees. All right, that's one vague version of the conjecture. The conjectures are precise. Here's another one of the conjectures in that same Fontaine-Mazer paper. Any irreducible representation that is geometric is attached to an automorphic representation of GLM Q. Well, this is a novel. Object here. Up until now, we were talking about geometry and arithmetic, that is to say, Galois theory, and now we're bringing in something, an extraneous point of reference. All right, and you can actually put these two together. It says that any representation that is attached in a whatever way that means to an automorphic representation actually comes from a smooth projective variety. So there are all these things are connected. The Galois group of the rational numbers, cohomology of smooth projective varieties, and these automorphic representations. All right, I'll try to make this more precise. Now, how would we go about attaching one thing to another at all? Well, the Galois group of Q bar of Q, the absolute Galois group of Q, is put together in a certain sense from the Galois groups of local fields, that is to say, p-adic fields. So not so long ago, we talked about about ZL. Here. And now we're going to take a different prime, P. We have infinitely many primes, so we can certainly choose two that are not the same. And so choose a prime, P. And now notice that a polynomial with rational coefficients also has coefficients in QP. Well, that's because I didn't say so, but the L-adic numbers, when I wrote them down, it could always contain, the L-adic numbers always contain the integers, and so the QL contains Q, and so does QP. QP contains Q. It's a field of characteristic 0. So now let's just forget about the rational numbers momentarily and just think about this polynomial as a QP, a polynomial with QP coefficients. Then the Galois group of QP bar over QP acts on its roots. All right, well, there are infinitely many primes. The starting point of algebraic number theory, right, first thing you learn in an algebraic number theory course, is that the action of the Galois group on the roots can be reconstructed from that of the Galois group of the p-adic numbers. But I don't exactly go so far as to say that. That's some part of this, the beginning of algebraic number theory, you get that. Then later you realize that everything can be read from this action. Well, when you remember that the étale cohomology starts from the Galois group of Q bar over Q, the L-adic representations, well, the L-adic representations on this cohomology are determined in some way by the representations of these p-adic Galois groups. All right, but L here is now fixed for the moment, and we're looking at all these different p-adic Galois groups. And how are these determined? Well, that's a long story. And instead of telling you how that story, I'll tell you a different story. So, an analogous story. It's often fruitful to think of an m-dimensional representation of the Galois group of Q viewing it as analogous to a local system. It better be m dimension rank m local system on a punctured algebraic curve. What is a punctured algebraic curve? Well, we take a Riemann surface, but think of it as an algebraic curve and just remove some points. You don't really have to remove the points, actually. We could have done, but it becomes more visually suggestive if we do. Now take a point, x0, which is not one of these points in what's x0, and we get a homomorphism of the fundamental group on the the fundamental group acts on the fiber of the local system at a fixed point. This is the general theory of local systems. And because we've decided that this is an m-dimensional local system, this automorphism group is isomorphic to GLM of Q if you choose a basis. All right? So we get a homomorphism from the fundamental group into GLM of Q, not QL, Q. All right? Now, if you draw a loop from x0 that wraps once around one of these points, and here I would, if I were in the same room with you, I would go up to the blackboard and actually draw this loop, but can't do that here, so you just have to imagine I'm doing that. There's a group, say gamma I, a loop, and well, you get an element in this automorphism group. Okay. And so we get an element in what we can think of as GLMQ. Now, the local Galois group is just generated by this loop. Well, that's not quite true, because this curve X can have a non-trivial homology, and we have to allow for that. But let's bear with me and just assume that we're x0 is very close to these points, so we're really just looking at a punctured disk in the neighborhood of xi, and then the local Galois group of the punctured disk is just z. And now, if we, instead of taking local systems with Q coefficients, we take local systems with finite, or I should have said L-adic coefficients, we have, think of it as the local Galois group is just z hat, the projective limit of all the finite local groups. Now, let's move from complex geometry to geometry over a finite field. Then the local Galois group has a three-step filtration. This is theory of the algebraic fundamental group. Suppose we take a point on a finite field, then there is a local Galois group acting on local systems. So how does that work? Let's suppose that K bar is, oh, this is a misprint. This should have been P to the R. I should have seen that, right? So suppose it has P to the R elements. Well, let's say we're over a finite field characteristic L for the time being. I hope the next slide will make this L. Then the Galois group of K bar over K prime is isomorphic to Z hat with canonical topological generator, the Frobenius. I would like this to have been P, but anyway, the Frobenius just takes T to the order, any element in K bar to the its power, its being the order of the fixed field. then the Galois theory of finite fields tells you that this Frobenius element precisely fixes K prime and it generates the Galois group topologically. Now, at a puncture xi defined over our finite field K prime, there are three non-trivial steps. So here's the Galois group. Let's call it gamma xi. That's the Galois group locally at the field. It maps to the Galois group of the algebraic closure of the field, which we've already seen as z hat, but it has a kernel. This is the Galois group of, another way of thinking of it is the Galois group of the completion of the function field of this algebraic curve at the point. But the kernel is just, we just call it the inertia group. It has a two-step filtration, the tame part and the wild part. Well, the tame part, now, all right. So now it's right. Now it is, so going back, I told you that it was characteristic L, but now it's characteristic P again, okay? My apologies for this. So the tame part is a product of ZL for L different from the characteristic of K, or K prime. And this you should think of as exactly analogous. This middle stage is a kind of product of L-adic completions of that loop that winds around the point in the complex curve. We're winding around that. The top stage, so this inertia group is a geometric part, and this is the, so if we were to replace K prime by its algebraic closure, the inertia group would still be there. It would be a subgroup, think of the algebraic fundamental group over the algebraic closure. The top stage is there because it's not algebraically closed. And then the wild stage is a pro-P group. And this is pro-nilpotent. It doesn't have a simple structure, so we won't try. But now, all that was just meant to motivate the Galois group of QP bar over QP. It has the same structure. It maps to the Galois group of FP bar over FP, and that's Z hat. This is just the same. This is the same as for the curve over a finite field, and it has a kernel, which is the inertia group. It has a tame part, which is exactly the same as what we had before, and then a wild part, which is a pro-P group, whose structure is still, even now, quite mysterious. All right. As in our example of the curve, the Galois group of FP bar over FP is generated topologically by Frobenius, which here is just taking T to the pth power. And now I can tell you what the local Langlands correspondence is. It classifies m-dimensional continuous representations of this Galois group in terms of something else. Well, it wouldn't be a correspondence if it didn't correspond to something. And it corresponds to something that is, or should be, for those of you who haven't seen it before, unexpected, because it classifies this representation theory of a Galois group, which is something having to do with number theory, in terms of analysis. Analysis on what? On a locally compact topological group, namely GLM of QP. Well, at least it's the same QP. So we can think of this GLM just as the algebraic, the matrix group, but it has a topological structure. And the analysis is going to be as soft as possible. So let me start with that. Well, let's go back to the familiar case. We looked at one-dimensional representations, and actually this is not very far removed from the cyclotomic polynomials with which we started. The Galois group, a one-dimensional Galois group, Galois representation, factors through an abelian quotient because its target is an abelian group. So what is the Galois group of the maximal abelian quotient or the maximal abelian extension of QP? Well, the answer to that is given by local class field theory. It says there's a canonical homomorphism from 2p star into this group with dense image. It contains the image of the inertia group. I said the inertia group contains the image of the inertia group. The inertia group is in here. It has an image here, which we can still call the inertia group. And then there's the element P. We recognize that, if nothing else. It's an element that is not a unit. It's not invertible. And P goes to the inverse of the Frobenius. All right. So that's local class field theory. Well, this tells us what an m-dimensional abelian representation corresponds to. I left out a word here. So a representation that is abelian, and I should say a completely reducible representation to avoid Jordan, not trivial Jordan components. So a semi-simple representation, a completely reducible representation that factors through the abelianization corresponds to an m-tuple of characters. Just, it's the sum of m one-dimensional representation. You've seen that each one-dimensional representation is a homomorphism from QP star, corresponds to a homomorphism of QP star. All right, so we have these chi-i's, m representation. And now what we're going to do is define a representation of GLM. We do this mechanically. So what do we know about G? So call it G to avoid taking up too much space. What do we know about GLM? Well, it has some subgroups, recognizable subgroups. We can consider the upper triangular subgroup of upper triangular matrices, that is 0 below the diagonal. And then it has a projection onto the diagonal elements, which is a homomorphism. So we call this A. The diagonal matrices form a product of m copies of GL1. So we define a homomorphism from B to QL star just by sending first the elements of B to m copies of GL1, and then for each copy of GL1, that's GL1 of QP, which is QP star. So AI of B is an element of QP star, and we take chi I of AI of B, and we take the product of those. All right, so now we have a homomorphism starting from so the Galois representation gave us a homomorphism from this upper triangular subgroup to QL star, but we want a representation of GLM, and we're going to do it by process of parabolic induction. Namely, we just look at all the functions from G to QL with the property that f of BG is equal to, well, I would like to be able to say that it's equal to chi of B times f of G. That would be the induction of this character, but so just a space of functions, and then G acts on the right by right translation. All right. Except we can't do that. We have to introduce an additional factor called delta to the 1/2, and I only include that for because I have a pathological tendency to be honest when I give mathematical lectures, even at the cost of clarity. So I'm putting this in, that is another homomorphism from B to QL star, which I encourage you to ignore, unless you already know what it is, in which case you don't need me to tell you. All right, so that's, and now we've got a homomorphism, a vector space, an infinite dimensional vector space, necessarily, and GLMX by translation. So, and now I can tell you what the Langlands correspondence is for abelian representations. To this homomorphism, we assign this induced representation, I of chi. And now, for various reasons, namely, we didn't have to consider only representations, homomorphisms to QL star. We could have considered homomorphisms to any L-adic field. So let's replace QL by its algebraic closure. And then an L-adic representation is a homomorphism from the Galois group to GLM of QL. But in fact, we could even replace QL bar by the complex numbers. Well, we'd have to take a deep breath before doing that, but let's do that. And since the theory is purely algebraic, the difference is inconsequential. All right, so you trust me. And so now to this Galois representation, this homomorphism of the Galois group to, well, we don't, the one difference is that if we want to get homomorphisms from the Galois group to C star, we'd better replace the Galois group by a subgroup called the V group. But, well, in any case, the difference is inconsequential. So we now have assigned to an abelian representation, a representation, an action of GLM of QP on a complex infinite dimensional vector space. Well, at the other extreme, we have theorem was proved some 20 years ago, twice, different ways, and then more recently, about 10 years ago, proved in a somewhat different way by Schulze. Suppose L is different from P. Now, there is a canonical projection between irreducible, continuous m-dimensional L-adic representations. So now the keyword is irreducible. What we saw before were the completely reducible representations, and now we're looking at the irreducible ones, m-dimensional, and irreducible supercuspidal representations of GLM of QP. Well, I'm going to have to tell you what supercuspidal representations are. And it's canonical. Well, it's canonical in the sense that it preserves natural invariance at both sides. It's also canonical in the sense that it can be constructed canonically in terms of algebraic geometry. But for some purposes, we'd rather forget about that and just think of it as determined by these natural invariants. Then, well, whatever supercuspidal representations are, they're the building blocks of the theory. So how can I explain this? To any m-dimensional continuous L-adic representation of the Galois group of QP bar over QP, you get an irreducible representation. Well, again, we really want to think of the completely reducible representations of this Galois group. And if you want to get a canonical bijection, we have to expand this class of representations to include the more general objects, basically because we don't want to we don't want the theory to depend on the field of coefficients. I told you it didn't matter whether the coefficients are QL bar or complex numbers, but that's only true if you include slightly more general objects. So you can think of the objects, the Federin parameters, as actual representations of a Galois group. And actually, we can, and the theorem is proved not just for the Galois group of QP, but for the Galois group of any finite extension of QP. And for that matter, it was proved even before this by Lemon, Rappaport, and Stuhler, if you replace QP by the local field F Q of T, which is, whose Galois group is the one that I talked about when we were talking about curves over finite fields. All right, well, to conclude this survey, there is a version of the correspondence. I put version in green as a way of warning you that I'm not going to say anything about what this means. There's a version of the correspondence when QP is replaced by R or C. All of the local fields, all the locally compact topological fields are on this slide. We've got the finite extensions of QP. We have the local fields of positive characteristic, and then the two Archimedean local fields R and C. All right. So there is such a correspondence. We get continuous representations, irreducible representations of the GLM of a local field. All right, well, now we want to get back to our original problem. Suppose we have an m-dimensional L-adic representation of the Galois group. It's continuous. As I said, the Galois group of Q bar over Q is built out of the Galois groups of the local fields. Well, what we really have are embeddings of the Galois groups of the local fields into the Galois group. These are not unique. They're not unique, but they are equivalent up to conjugation, and that's all that matters for the purposes of what I'm about to say. So when we have such a continuous representation, we can restrict it to this Galois group, call it rho P, and this restriction is unique up to conjugation. So this as an equivalence class of homomorphisms, it's well defined. Now here's where we need to think momentarily about topology. If P is different from L, we have the local Langlands correspondence. And thus, by the recipe I sketched before, we get an irreducible representation, which we'll call pi rho P, of GLM of QP. But if P equals L, well, here all of a sudden, the representation, well, I said it's continuous, and it's continuous in a way that really does depend on L because of this wild Galois group. If this were C, then the image of the wild inertia group would be finite. But that's no longer the case if P equals L. So we need to make it a hypothesis. And what is the hypothesis? Well, I don't tell you what the hypothesis is. I tell you what it's called. The hypothesis is that rho L is of de Rham type. And this is defined by Fontaine's p-adic Hodge theory. And then we have a theorem. We don't tell you what de Rham type is, but we tell you what it's good for. If rho L is of de Rham type, then L-adic Hodge theory attaches a Federin parameter to rho L. And thus, through this extremely elaborate process, we get an irreducible representation of GLM. We go first through all of Fontaine's theory, and the proofs of which were completed about 20 years ago. 15, 20 years ago, and thus we get an irreducible representation. Now, let's return to our original continuous representation rho. We have its pi of rho p. I just said that Fontaine gives us a pi of rho L. So, a new definition. The representation rho is geometric if first rho L is of de Rham type, which means we get a pi of rho L, and then, which you wouldn't have had otherwise. And then for all but finitely many p, rho p is trivial on the inertia group, which implies, among other things, that pi of rho p is one of those principal series representations, those induced from the upper triangular subgroup. All right, so a geometric rho gives us a collection pi p for all prime numbers p, and for all but finitely many of them, they are what's called unramified. Now, another part of Fontaine's theory tells us that we get a representation pi infinity of GLM R. I could have just tacked that on here if that's also a consequence of being of de Rham type. So now, let's look at an Adel group. This is we have the Adels. We have GLM of R. That's just a familiar matrix group. We have a GLM of QP. That's a less familiar, but still a matrix group. And we take the product, but we don't take the full product. We take the restricted direct product, which means that for all but finitely many p, these elements are in GLM of ZP. I won't write that down. And then we take the quotient of this by GLM of Q. There should have been an extra parenthesis here. Well, we have an action on the right of this space called SM, S for symmetric, and GLM R acts and GLM QP acts. And I define a representation rho to be automorphic if this collection so we can take the tensor product of these pi p and pi infinity. Again, it has to be a specific kind of tensor product. And the representation is automorphic if this collection occurs as a direct summand in this space. Now, the L2 space. Now, first of all, this is slightly more restrictive than the usual definition, but let's not worry about that. Secondly, we can't actually take an L2 of this space, or it's not very helpful to take an L2 because there is the multiplicative group of R that acts, and so it has a copy of R in it topologically, and that makes it too big. So L2 includes the theory of Fourier transforms on R. So we take the quotient. For example, we can take the quotient by the multiplicative group of positive real numbers. You can think of that. Then so it's a quotient of this, or some other kind of equivalence relation. And now I can tell you what a more precise version of the Fontaine-Mazer conjecture. Any irreducible representation, this should be a QL bar, that is geometric is automorphic. All right. So again, there are quite a few misprints in these notes, but anyway, you'll correct that. Put a bar over here if you're taking notes. Well, what is this object? Let's think about this L2. This pro-manifold is homogeneous for the action of this Adel group. That's what I just said. And we can think of this as the analog of the space of functions on infinitely many copies of the circle. There's infinitely many copies of something, which is a representation of the compact group the circle, U1. The decomposition of functions on the circle under the action of the circle group is the easy part of the theory of Fourier series. And so this is a non-abelian analog of Fourier analysis. And it's not only legitimate, but perfectly respectable to study the decomposition of this the L2 space of this homogeneous locally symmetric space purely analytically, without any reference to number theory. Okay, I'm just saying this. And so now, if you want a 2-sentence summary that you can take home, or you're already home probably, so you can exchange with your friends. To each integer m, we assign a promanifold that's homogeneous for a very large group. And then I haven't got to the end of the sentence. Then the theory of geometric Galois representations is conjecturally, because it's still a conjectural program, encompassed by non-abelian Fourier analysis on these homogeneous promanifolds. All right, so there's a summary of Langlands reciprocity. However, so happens, and this is a matter of even greater mystery, there is a large part of the L2 space that has no relevance whatsoever to Galois representation. So one wonders how one can describe them, but we're not going to talk about that today. All right. Well, now let me say something about when you can complete the Langlands program. Although this is not going to be directly relevant to my talk. Well, suppose we're back on the punctured projective line, but now we're over the finite field FP. Well, the field K of X, which is FP of T, is the global field. Now, since we're already in characteristic P, we can choose an L that's different from P. We're not going to be worried about p-adic representations. And now we can replace the topic of number theory, the Galois group of Q bar over Q, and its homomorphisms to matrix groups, by an irreducible m-dimensional L-adic local system called lambda on X. What is this? This is a representation of the Galois group. I mean, the fundamental group of this, the geometric fundamental group of this, the arithmetic fundamental group of this punctured projective line is here in arithmetic. We have generic points. So we can take a fundamental group at the generic point, and this is the Galois group of the algebraic closure of this field, which with values or the separable closure, I should say. We're looking at homomorphisms into this group. And because we have punctured it, we're assuming that this is ramified only at the points we removed. It's a local system. It has ramification. That is to say, the inertia groups at these points may have a non-trivial image, rho of the inertia group. At xi may be non-trivial. The inertia groups at the other points act trivially. And to return to complex geometry, the analog is in a linear system of differential equations with singularities only at the punctures. That's the Riemann-Hilbert correspondence. All right. Well, as before, to such a lambda, one attaches a representation pi sub x for each point x in the projective line over FP bar, Kx is the field of constants, the field of definition of the point x, which is a finite field. We take a representation, but it's instead of being the local Langlands correspondence is known, so we have a homomorphism, a representation of the local Galois group, and therefore an m-dimensional representation, and a representation pi x of GLM, which we can think of as a complex representation. Theoretically, we should have a QL bar representation. We could call it a complex representation. And note that we include the singularities, so it's a ramified representation. That is to say, it need not be principal series and need not be induced from the upper triangular subgroup. Okay, this is the coordinates in the finite field. So for each x with coordinates in kx. And we can define automorphic representations in this setting too. It's automorphic if it occurs in the L2 of S of mx, where, again, now I'm not telling you what this local system is. I mean, this locally symmetric space is. Again, there's an equivalence relation, modulo something. The space is totally disconnected. And not only that, it is in bijection with a set of rank m vector bundles on the curve x defined over the finite field with trivializations at all points. That's the way it's set up. Well, here's the theorem of Laurent Laforgue. Every lambda is automorphic. And actually, he wasn't concerned only with the punctured projective line. His theorem states that if you take a local system over a punctured curve, algebraic curve, any algebraic curve over any finite field, a local system, an analytic local system is always automorphic. That is to say, if you attach to it a representation of the Adel group, you would get this representation of the Adel group occurs in the L2 space. Now I'm almost at the end. Suppose we replace rank m vector bundles by principal G bundles, where G is a reductive algebraic group. So these are just principal homogeneous spaces over X, where G acts. Then one gets an analogous space of automorphic forms, L2 of bun X of K, where this is, instead of putting GLN, we take, or GLM, we take products of G, whatever G is, the points of G with values in the local field, equivalence class modulo the diagonally embedded group of points over the global function field. And Vincent Laforgue proved a theorem that gives half of what his brother proved, but in fact, but for a general group. All right, but now, what corresponds to lambda? Lambda was a local system. Instead of a local system, we get a lambda Langlands parameter, which is a homomorphism from the fundamental group to the Langlands dual group. And what Vincent Laforgue proved is that to every irreducible constituent of this L2 space, actually, what he proved is that if you look at the cuspidal constituents, which I won't try to define, to each cuspidal constituent, you can assign a homomorphism from the fundamental group to the Langlands dual group. And that's the end of my slides.